Hello everyone, it's May the 3rd. Alright, let's take a look at today's Dota 2. I never really played Dota myself. I used to watch other people play. Yeah, it's interesting, just like watching sport, right? You watch people play and it's interesting. So that's all I have. And it's too complicated game for me. I'm not really a person for games. Anyway, I feel like I've done this before. Radiant and Dire. I don't know they're called that. And the things I watch is always in Chinese. Alright, it doesn't really matter. What do we want is coming from two parties, and now the Senate wants to decide on a change in the game. The voting for this change is a round-based procedure. In each round, each senator can exercise one of the two options. Ban one senator's right. A senator can make another senator lose all his rights in this and all the following rounds. Announce the victory. If this senator found the senators who still have rights to vote are all from the same party, he can announce the victory and decide on the change in the game. Given a string Senate representing each senator's party belonging, the character R and D. Is that Republican and the Democrats, huh? Yeah, I just realized that it's R and D. Radiant is about Republicans, Dire is Democrats. If there are n senators, the size of the given string will be n. The round-based procedure starts from the first senator to the last in a given order. This procedure will last until the end of voting. All the senators who have lost their rights will be skipped during the procedure. Suppose every senator is smart enough and will play the best strategy for his own party. Predict which party will finally announce the victory and change the Dota 2 game. Output should be Radiant or Democrat or Dire. So what's the rule? Each senator can exercise one of the two rights. It can ban one senator's right. It can make another senator lose all his rights in this and all the following rounds. Which means if it's your round, he can ban someone, or he can announce victory. If this senator found the senators who still have rights to vote are all from the same party, he can announce the victory. Oh, that's basically nothing. That's just end game, right? If only the same party remains. Okay, so for R and D, for R, I just ban D, and then the result will be R, right? The first senator comes from Radiant, and he can just ban the next senator is right in round 1, and the second senator can't exercise any rights since his right has been banned. And in round 2, the first senator can just announce the victory. So in round 1, in each round you can do this, and you can go from left to right. Okay, so in this, yeah, I definitely done this before. The first senator comes from Radiant, and he can just ban the next senator's right. And the second senator can't exercise any rights anymore. And the third senator comes from Dire, and he can ban the first senators in round 1. And in the second one, the third can just announce that is correct. I don't remember how I solved this. What do you think? So you can say for the first one, they definitely want to ban, right, somebody else. And then for the next one, if so if you are R, you try to remove these, right? You try to remove these. You know what? I think this, I don't know, man. It's this 10 to the 4. Is that DP? How would you imagine DP to work? Well, DP will work. Because you're banning people, right? You're banning people. That means you have a state. Oh no, it's 10 to the 4th. There's no way we can do state. Maybe greedy? I mean, if you are the first one, you will try to ban a D, right? And you should ban a D as early as possible, right? Because if you don't ban it early, so here's basically like if we have R, D, R, D, D, I don't know, just randomly put something out. And you are here, right? And if you ban a D later on, then this D can ban an XR, then this D can ban XR, right? Then the D will win. So you want to remove as much power as possible. So I'll ban this, right? That's a good move. And for this, they will ban the next one. So now only one D alive, and it will ban this one. And then this R will ban the first D. Then we're gone. So is that how it goes? I mean, we can try to see if this is D. I think this one will be, no, this one will be radiant. Right? If we go RDR, DDR. Everybody playing the most optimal. It just means, right? Because that's the optimal. If I have like D, I don't know, D, R, D, R, R. Same numbers, right? So for this R, again, if I ban the D later on, then I have more chance for the D to ban my R. If I ban R early on, then I reduce the chance that the D can ban my compatriot, right? So I ban this. And for D, it's the same thing. If I ban it later on, then somebody can ban me. So for here, I need to ban this. And for this D, I'll ban this, right? And for this D, I will ban this. And for this R, the next round, I will ban this. And for this D, there's no more R, but we come back, I'll ban this. And for this D, I can announce. So this one shall be dire. What's this? R, D, 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 R, D, R, R. If this is right, we can try to write this algorithm. Yeah, it's dire. Yeah, this is dire. So, what do you think? Well, what I think is I need to know their indices. Now, how can we make this faster? I mean, I don't know. Like, when there's a start, right? I can say the current position, I should say R equals 0, and D equals 1. That's the current position, right? So whenever I'm at R, I look at D, right? And I say I'll ban this. And then we can just ban it. And D will move on to the next D. So in this case, D will move on to 2. And R will move on to the next R. So R will move forward. So we'll move on to the next R. 1, 2, 3, 4. We'll move on to 4. All right? And then D will take the first R. So we'll remove this. And R needs to move on to the next one, which is 6. Right? And D will move on to the next one, which is 3. So next turn is D again, because the smaller of the two goes first, so D again. So it will remove R. So we'll remove this R, so R move on, R becomes 7, and D move on to 4. 0, 1, 2, 3. No, D's not from the next D is 5. And still D's move. So D will move this. Then R will wrap around. Right? Or wrap around. Now R will become 0. Now it's R's turn, so R will move 5. Oh, R shall not move 5. Dang it. So when some go into the start, I need to reset. So the D need to reset. D need to reset. How do you reset? I don't know. I feel like if I reset, I have to go through everything, right? I mean, reset definitely works. Reset, this one will go. Oh yeah, because I ban something, right? And R goes, and D need to go forward. So D go forward, will go to 2, right? And R will ban this D. And D will move to 3. R will move forward. Oh, R move forward. It will move back to 0. But it should be D's turn. Ooh, how'd you handle this? Right, R moves forward. And there's nothing, right? There's nothing for it to move. So I shall actually move to outside, right? 0, 1, 2, 3, 4, 5, 6, 7, 8. Maybe I should move to 8. I move to 8. Then it's this turn. And then when this goes to 8, then we reset. Yeah, that will work, right? And D... you should just keep going. It just should be 8, right? R is 8. And then it should do this. And then I can do mod 8. And I know where they are. So this will ban this. And this one will... Basically, there's nothing left. So this will become... Go forward to 5. And then this one can denounce. But I feel like shall be the easier way to do this. Can we just avoid constantly moving around? Like, how many rounds do we even need to move? But maybe that is the case. I mean, if you don't move around, how would you want to do it? If you don't move around, I might be able to, I don't know, set another... Because I was thinking maybe we can shrinking the size, you know? If I start with this, right? If I start with this, and then I create another array, right? R is the first one, and we'll remove this. So R will put in, right? And then it will go to D. This D remove, and now I mind this D. So this D will remove, so I'll put this D in, and then we'll remove this R. And now we go to next D. So this D in, I remove this R, right? And we'll have this D, and then we'll remove this R. So this D will remove this R. Now everybody come to the end. So now we go back. We start from here, right? And then we'll say a new array. We say this is R. We'll remove this D. Now is this D, right? We'll actually go around. Oh, you'll go around. But I already put this down. Yeah, this is not gonna work. So I just go round and round, see if it's fast enough. Maybe it is. Who knows? I mean, this is greedy, right? So what do you need to know? I need to know the total number of R and Ds. Well, for one thing, we can say count R equals Senate count R, right? Count D equals Senate dot no, len senate minus count r, okay? And then list equals list senate, because I need to change it. Now we need to go find the start. Say while count r and count d, okay? So the start, we're gonna say r equals d equals 0. And now we need to move to the first one. It's like reset, right? It's like reset. We can say, wait, hold on. No, I just need to, while I can go list r is not equal to r, right? R plus equal 1. While list d is not equal to d, d will plus equal 1. So now they settle on the first one. Then we will go with the smallest, right? The smallest will move first. Okay, the smallest will move first. How are we going to move? Basically, let me say if r is smaller than d, okay, then r move first. Then what does r do? R will remove a d, right? Then we'll say list d will equal to this, it being removed. And count d will minus equal 1, right? And then what? And then d need to move forward. Then we say while list d is not equal to d, d plus equal 1. But here is the thing, we have to do something here. N equals to len senate. All right, we have to mod it because I want the d to keep going. So basically d can be mod n. If it's not equal to d, we'll keep going until it is equal to d. That's the next d, right? And of course, we have to move r as well. Which means, because I used r, right? Now r plus equal 1. Then while list r mod n is not equal to r plus equal 1. Else list r is equal to this, count r minus equal 1. Ah, that's very interesting. I probably can do this at the very beginning, right? Maybe I can do this at the beginning, you know? Of course, not doing this. We just do this. And then I don't need to do this, right? And then if this, and then r plus equal 1, else this, d plus equal 1, right? Once I'm done, I reset, do it, reset, until one of them becomes 0. Now when it comes out, we should return radiant if count r, else dire. Okay, I have a couple of test cases. I have rd, right? This should be radiant. I have rdd, that should be dire. And I have these two. I don't remember. Is this this is radiant, I think. Yes. And this is dire. Okay. Senate. check this. Predict party Senate. Index out of range. Oh, of course it's out of range because I forgot to mod. Yep. Okay, you want to try... Now we can try. It's R and D, right? Okay. Oh, and I think it's LeetCode's favorite thing. Not really. I don't know. Oh, shoot. This is not right. How about just 1, right? We'll make sure 1 is always right. That should be good enough. I think that is correct. Yes, told you. Told you done this before. Runtime's not as good as it used to. Interesting. Alright, I need to check the previous method. 6:49. Greedy. Each round, the player, the senator, bans the closest, right? The next closest senator of the opposite party. Okay, let's see. Did they change the 82 test cases? Oh, they added 1 more test case. Oh, I reported this. That's very interesting. Oh, is that the new test case I added? Oh, interesting. I forgot. That's the one. That's why I remember it, because I made a contribution to this one. Yeah, that's my initial a very terrible one. Each center bans the first enemy to its right. Oh, a deck. Look at that. Oh, I see. This is genius. This is genius. I think my current solution is not that bad, but this is definitely also pretty good. Using deck. Yeah, and then everyone, you just pop. Because this, yeah, because you start from this, will pop the closest, right? And once you pop, you move that to the end. And you pop this, you move to the end. You pop this, you move to the end. Oh my goodness, this is beautiful. This is beautiful. Genius. This is genius. Oof. So good. Yeah, that's how I earn a lot of LeetCoin, I think, from this one. I don't even know what that solution is, but oh, the deck ones definitely. But at least we have something, right? This the solution is not that bad. Using deck to implement the wrap around. Very genius solution from this discussion. All right, so I don't even need n. All right, all we need is dr equal to deck for I. I might do it this way. Dr rr deck r deck d deck equals deck and deck for I as in enumerate senate dr if s is equal to d. Nah, I don't like this. Stupid. I just do deck for I as in enumerate senate if s is equal to d. Then we append this. Alright, now we do the same thing. Deck d. Oh, there should be r. My bad. Alright, and then we just say while dr and dd rd and dd. Then we can say ri equals to rd dot pop left. Di equals dd dot pop left. Because no matter what, they'll have to be popped out. Right? If you go with r, you pop that, and then you have to pop the other one. If you go this, you have to pop, and then you just decide which ones go to the end. If ri is smaller than di, then rd dot append. Alright, so this one done, we go to the back. Right, else dd dot append di, right? And you wrap around. But what if, hold on. What if one wrapped around? Actually, I don't know. Wait, is this right? What if one wrapped around and the other has more to go? Oh, that's fine. And it will pop out. And wait, hold on. I have a question about this solution. What if I have something like, I don't know, RDDD like this? Right, on the deck I have 0, the other has a 1, 2, 3. Okay, I pop both out. Then this one's gone, this come here. And then I pop out. Right, so R will come on this one. And then I pop out. It's 0 and 2. And if it's 0 and 2, I'll say 0 is smaller. Then we give this one, and then we'll pop 2. Wait a second. How does this one work? Oh, wow, I was like, yeah, it doesn't make sense. Now it makes sense. Yeah, that was my bad. You have to plus n. That's true. Now that makes sense. And then we shall return radiant if rd else dire. Yep. Now this is a very good solution. Do you think it'll be faster? I don't think so. I just said it. No, it is. It is because it's less going around. Yeah, less going around. Definitely faster. Yeah, the question like this, I don't know, like what's the runtime for this? I mean, O-N. How about this? Well, everybody gets popped, put back, popped, put back, popped, put back. I don't know. Like each round, you have something gets popped. So you're reducing. Right, the next round, you're reducing until you have only one left. What's the runtime for this? I'm not sure. I was suspecting it's O(n) squared. I mean, this is definitely O(n) squared, right? This we can understand because every time you have to go around the whole thing, you don't know how many rounds you have to go. That is O(n) squared. What's this? It doesn't matter. I like both methods. That's O(n) squared. This is also O(n) squared. Not a full O(n) squared. That's why it's like 10 to the fourth. If it's full O(n) squared, I don't think it will work. But it's not a full, so it's good. Okay, so that's that. Maybe I'll just read a little bit, but I don't really have any Ghana to do this today. Let's see. Count number of possible root nodes. Alice has an undirected tree with n nodes labeled from 0 to n-1. The tree is represented as a 2D integer. Edges, that's fine. Alice wants Bob to find the root of the tree. She allows Bob to make several guesses about her tree. In one guess, he does the following. Choose two distinct integers, uv, such that there exists an edge in the tree. He tells Alice that u is the parent of v in the tree. Bob's guesses are represented by a 2D integer array guesses, where guesses indicate guesses u to be parent of v. Alice, being lazy, does not reply to each of Bob's guesses, but just says that at least k of his guesses are true. Oh my goodness. They're a jerk. At least k. So it could be more than k. Given the 2D integer arrays. And the integer k, return the number of possible nodes that can be the root of Alice's tree. If there is no such tree, return. Oh, that is very interesting. Number of possible nodes that can be. Oh my god. My goodness. I mean, you can draw all the trees out like this, right? You give it the edges, I have all the trees. And the guesses is 1, 3, 0, 1, 1, 0, 2, 4. So for each tree, each possible tree, at least 3 of these has to be right. Which in this case, right? So for tree number 1, right? For tree number 1, 1, 3 is correct. 0, 1 is correct. 1, 0 is wrong. 2, 4, so this is good. This, 1, 3 is right. 0, 1 is wrong. 1, 0. Well, one of these will be correct. Right? And then one of them will definitely be wrong. The other will be right. So this is 1. So I just need to check if these two are correct. 1, 3, 2, 4, that's correct. 1, 3, 2, 4, that's correct. And 1, 3, oh, is wrong. 2, 4 is wrong. So these two are wrong. So we can definitely analyze the guesses first, right? Okay, analyze the guesses. Guesses is unique. It's the edge of a tree. Okay. So for this one, yeah, I can take a look. I already know the answer. K equals 1. So at least one of them is correct. So if one of them is right, then it's right. So 3, 4, that's right. 1, 0, that's right. 2, 1, that's right. 3, 2, that's right. 2, 1, that's right. What do you think? What do I think? Man. Reuse the results, right? That's what I think. Because when you set 0 as a root, this part, right, and this part is the same, which means if 0 is correct and the correct edges are in the bottom, then this one is correct as well, right? So what we can do, let's say I put in 0, and then we can see how many are correct. So we have 3, 4, right? 3, 4 are correct. So which means 0 as a root is correct, 1 as a root is correct, 2 as a root is correct as well, 3 as a root is correct, right? Because 3 and 4, and 3 and 4, 3 and 4, 3 and 4. So by doing this, we already get all of them. So now we just need to go 4 as the root, right? And the 4 as the root, I probably have to go through the whole thing, and I can find 1, 0. But we can also say when 0 we have 3, 4 is correct, but this is wrong, this is wrong, and this is wrong, right? Which means if you start from here, then this will be correct, right? You start from here, this will be correct. So I kind of feel, this is what I feel, maybe we iterate through 1 would be sufficient. Don't be too certain. Oh, might not know. All right, let's try this. So we have 0, 1, 2, 4, and 3, right? I guess it's 1, 3, 0, 1, 1, 0. Yeah, but this one is okay. 2, 4. We know this is gotta be 1. At least one of them is right, so we don't need to know. And the minimum is 3, so we know this must be right and this must be right. So we go from here, right? And we see, okay, 0, 3, right? So this is correct. So with the 0 as a root, this is correct, and 2, 4 is also correct. So in this case, this is right, this is right. So if I can maintain this relationship, then it should be fine, right? That's the only key. So if we go 1 as the root, because from you go from 0 to 1, right? You go from 0 to 1, so 1 as a root. So 0 as a root is good, 1 as a root is good, right? And if you go 2 as the root, how do you know that 2 as a root is good? Because you go down, right? You come from just go down, and you say 2 as a root is good. But 3 as a root is not good, because if 3 as the root, it reverses 1, 3. And 4 as a root, it reverses 4, 2. How do we code this? What do you think? I mean, we're going to have a bunch of these edges, right? And then if you have a tree, and you will know like some edges are correct, some edges are wrong, right? Then what? Okay, so you start from a root, and then yeah, let's say we need certain number. I can produce all the parent-child pair for this. Okay, let's say we produce all the parent-child pair. I know all the parent-child pair, and I compare to this. I know certain pairs work, certain pairs don't. And from that, how can we translate? I mean, as the tree goes on, right? As the tree goes on, because the tree, it goes on, right? It goes on. It doesn't really matter. It can go on, but it's layer by layer, right? It's layer by layer, which means whatever parent-child pair, we start from here, all the child and parent pair, and we go to the second layer, right? If these become root, then everything down maintains the order of child-parent pair, but everything above will be reversed. And then you go down to this level. But that's actually not entirely true, right? It's just this and this will be reversed. If my parent is here, right? If this is the parent, of course, all of this are maintained. But on the other hand, this one is reversed, right? This one's reversed. But this to this is maintained. Because this is on the same level, okay? This is on the same level, so this is still maintained. This to this is wrong, but this to this is maintained. So are you saying the only thing that's wrong is going to be the one that's straight up to the current root, right? If I say this is the root, okay? If I say this is the root, then its parent, definitely, it's gonna be wrong. This pair will be wrong, and this to its parent will be wrong in the current, right? In the current path, its parent will be wrong. So let's say, because it's a tree, right? It's only one route to. So for each, let's say for each node, I have a path, right? I have a path. For each node, I have a path. Then what we're saying is, when this node serves as a root, the only reversal of parent-child relationship happens on this path. Anything else stays the same. That, I think, is a very important discovery. Even if we are here, right? If you are here, the only thing changes is this path, right? This path changes because this is parent-child, parent-child. But this remains the same, this remains the same, and this remains the same. Therefore, what I propose is we will go probably DFS, right? And we can reach a node. And I have a path, right? I have a path which can be let's say, just I to j, and I say n0 to n1, n1 to n2. It can be a list, right? Now at my current node, and I want to know how many pairs, right? How many pairs will this have? But wait, hold on. Can we probably need the total number of pairs to start with. Okay, let's say we have the total number of pairs, right? We traverse the tree once. We get a total parent-child pair, starting from one root. Total pairs, okay? Now, we have a total pairs. And then we traverse again, but this time we do the path. So we have the path, right? This is the path. This is the path. I mean, we probably can just do path like n1 and 2. Maybe we can do this way, right? Then we always know it's go this way, right? And now I have the total parent-child pairs, right? We have the total pairs. And then what I know is among the total pairs, right? These needs to be reversed. And the remaining will be okay. So what I can do, right? What I can do is to find in this total pairs how many matching the guess, right? Let's say in this total pair I have, I don't know, x matches, all right, x matches. And then now I have my current path. Then I want to see how much this path will match. So I'll reverse it, right? I'll reverse it. I'll reverse the path. So I know how much it matches. And then, but some might match one and don't match the other. Now that is a difficulty. That is a difficulty. How do we counter that? Basically, we're saying just we traverse to the current, right? We traverse the current. I want to know how many total matches do we have? How many total correct do we have, right? That's what we want to know. How many total correct? So I have the total correct. Then I start from the beginning. And then I go 1, right? And then we're at that node. And I have 1 reversal. And then I check if that is in the guesses. If it's in the guesses, then I need to minus 1. The total correct into minus 1. Right? Total into minus 1. And then I do another one. If this is in the guesses, I need to minus 1. If it's not in the guesses, then it will be reversed. Right? If it will be reversed. And if the reverse is in the guesses, then I will plus 1. Then at each node, I will have the total number of guesses. You know what? We might actually solve this. I think this is legit, but I don't want to code it today. I don't. I have another thing to do, so I'll just end it here. And I think this is legit. This is legit. You know what? Let me just put one more, so that maybe tomorrow I remember. All right. So step 1, we will traverse the tree with starting with any node, starting with any node as root. and count the total number of correct guesses. Right, call it T. Second, starting from the same, right? Starting from the same root, we DFS again, right? But this time, each new edge is visited, we check if UV is in the guesses, right? Now, since this path, since we want to treat U, no, not U, V as the new root, the path shall be V to U. Thus, if UV is in the guesses, we remove the total guess by 1. All right. If VU is in the guesses, we add total guess by 1. Right, and then we just, you know what? I'm actually interested. Let's see if we can get something out really quick, because I feel this one is very opportunistic, you know, very, very much. But of course, I mean, we have to go from collections, default dict. We always need default dict for graph, and graph equals default dict list. Okay. For AB in edges, graph A dot append B, graph B dot append A. Okay. Then we say T equals 0. Okay. Then we have, oh my god, we need the 2 DFS. Actually, self.t. Okay. So DFS 1 node, don't return anything. Okay, so what do? We basically just traverse, right? I'm at my node, and we need to change guesses, right? We can change guesses set equals a set. For AB in guesses, I'm going to change that into AB. Okay. Then we say for child in graph node. We probably need parent. Right? If child is not equal to parent, then we are saying self.t plus equal to node, this is the current parent, to child, right? Node to child in guesses set. If it's in, then we have the total correct guesses, right? And then we do DFS, child and node, right? we just do this. So this will give us, so we can actually call DFS1. Actually, we need the DFS2. Def DFS2 node parent and what? And the current correct guesses. All right. Again, it's going to be none. And we need self.t total number of correct guesses starting from some node as root. Self.res, this is just a result. Okay. Now, it's if current correct guesses is larger or equal to k, right? Then node is good. Then we say self.res plus equal 1. Okay. Then we need to go to then what's then? Then we will go to, because I'm at my current node, right? I know the current correct guesses. Now I need to go to my child. Then I need to give my child the current correct guesses. So child in graph node, if child is not equal to parent. Okay, so now the parent child will be reversed, right? Will be reversed. So we shall say the next correct guesses, right, shall equal to the current correct guesses plus int something minus int something. So plus what? Plus if child to parent is no, child to node, right, is in guesses set minus node to child in guesses set. Then we'll do DFS2, this is DFS1, child, node, and this one, next guesses. Right, this is the next guesses. Then we'll do this, right? So now we do DFS 0, parent is a -1 because everybody is larger than 0. Yes, so we do this. This will give self.t, right? And then that's DFS1. Then we do DFS2. Still start from 0, parent. Current guess is a self.t. And then we'll return self.res. Okay, let's give this a shot. If it's not right, then that's a good cue to end today. If it's correct, then hooray. We'll move on to our next task with great confidence. Yeah, confidence is very important, especially these days when my research is kind of hitting a bottleneck. So if this can kind of restore some confidence in me, all the good, all the good. Looks good. I'll try this. This shall look good. I hope it passes. Very good. One shot. I mean, we start on the right route, so yeah, intuition, right? The most important intuition is that say we pick 0 as the root, right? Now, as we DFS from 0 to another node, say 2, if 2 is considered the root, then all the parent-child order of the edges when 0 is the root are maintained except from the edges in the path from 0 to 2. Therefore, if we can compute the total number of correct guesses of parent-child orders when 0 is the root, we can progressively compute the total number of correct guesses as we traverse from 0 to all the other nodes. All we need to do is that each time a new node is reached, we check the last edge, right? We check the last edge. If that last edge is in the last edge in its original order is in the guesses, then when the new node is the root, that edge will be reversed, right? And won't be a correct guess. So we deduct from the total correct guesses. But if the reversed edge is in the guesses, then the total correct guesses add 1, right? By doing so, we obtain the total correct guesses for each node, right? For each node when we reach it, as if it were the root when we reach it during DFS. The implementation below contains 2 DFS. The first one obtains the total number of correct guesses, and the second one progressively computes the correct guesses for each node. ON. I might want to read this. So yeah. Trivial solution. You think this is easy? I mean, it's not hard, but I think this intuition, it's not the easiest to come with, right? I think I got lucky today. For whatever reason, it just immediately reached there. All right, anyway, That'll be it for today. I will see you guys tomorrow. Adios.